Problem 85. The state of stress at a point is characterized by the stress tensor S, given below. This is tensor S. Now consider the vector n and m given by. This is vector n and this is vector m. Are the two given vectors n and m eigenvectors of a tensor S? Find the principal stress for the given stress tensor S.
If n is an eigenvector of the tensor S, then we can say that tensor S applied over vector n will be the same vector scaled, but it's a scalar called mu. This will be so applying tensor S over vector n will get which give us this vector, but we can factorize a and we get this new form where we can recognize this is a scalar which will be the eigenvalue u1, and this is equal to n. So we prove that n is an eigenvector of tensor S, and we call it n1. Then n equal this vector is an eigenvector of tensor S, and u1 equals a, the corresponding eigenvalue. Okay. Now we need to prove the same for vector n. Stop. And in this case we get this vector, which is not the vector n as we expected, or it doesn't look like. So let's do another thing, finding the eigenvalues of tensor S. For that we can determine tensor S minus mu times the identity matrix, all this one equal to 0. Resolving this determine, we get the following cubic equation: u cubic minus 6 u squared plus 6 before mu equal 0. Factorizing the equation, we get this expression, which gives us the three roots of the cubic equation. We call it u1 equals a, mu2 equals a, and mu3 equals 0. Therefore, we have two equal eigenvalues let's find the eigenvector for mu3 equals 0 applying this expression to find the vector n3, we put equal to 0 or vector 0. Systems of equation we can get from the first row multiplied by the column 4 and 1 minus 4 and 2 is equal to 0. That gives us n1 equals n2. On the third row we get a times n3 equals to 0, and that gives us that n3 is 0. Now, using the other relation about the length of the vector, which is a unit vector, and v, the sum of the components, square of the components equals to 1. Square. Using the expression we found before, where n2 is equal to n1 and n3 is equal to 0. So, doing the operations, we finally get that n1 is equal to 1 over square root, and this is the same for n2. Then vector n3 is equal to 1 over 2 square root, 1 over 2 square root, 0. And this is at the same time the vector n that we got at the beginning. So we have proved that vector n also is an eigenvector of tensor n S, and its corresponding eigenvalue is u3 equals 0. So far we have found then u1 equals 8 and its eigenvector n1 equal to 1 over 3 square root minus 1 over 3 square root minus 1 over 3 square root. And also for u3 equals 0, we found n3, which is 1 over 2 square root 1 over 2 square root 0. Finally, we can find eigenvector n2 doing the cross product n3 cross n1. Then that will be equal which give us 1 over 6 square root negative minus 1 over 6 square root and minus 2 over 6 square root. The length of this vector is equal to 1, and then we conclude that n2 is the third eigenvector and is corresponding eigenvalue u2 equals